So here is a valuation theorem. Can you read all of it? I apologize. As I go lower down the board, my handwriting seriously deteriorates. But at which this condition in 3 is met for all n greater than capital N. Okay. So pi defined by step 4 is epsilon optimal, and Vn plus 1 minus V star is less than or equal to epsilon by 2 when 3 holds. So when this holds, Vn plus 1 is epsilon by 2 close to V star, right. So what is it? A and B are kind of easy, we have already seen that. A and B are essentially Banach theorem, right. So Banach fixed point theorem, the Banach fixed point theorem gives us A and B, correct. What is the difference between C and D? Why do I have 2 of these things? Don't they look contradictory? They look contradictory, not contradictory per se, but redundant. Yeah, anyone gives me the right answer, I will give you a bonus mark. That essentially means I have been following whatever I have been saying so far. So Pallavi, you will have to take down your roll number and note down that. Now I got their attention. Huh? So people who don't know, the class averages for my quizzes tend to be in like 2 or 3 out of 20, huh? Or 50. It doesn't matter what the denominator is. The numerator doesn't seem to change. But so every mark matters. So tell me, what is the difference? Why do I need C and D? Sorry? It's epsilon optimal. Epsilon optimal means it's close. Maybe if I say it in a different way, then you will get it. So what I am saying is that V pi minus V star is less than epsilon. Here I am saying Vn plus 1 minus V star is less than epsilon by 2. Remember, my space V does not necessarily contain only value functions, it is just a space of functions, right. Vn plus 1 need not be the value function corresponding to the policy pi. Even though I recover pi by being greedy with respect to Vn plus 1, does not mean if I actually solve for value of V pi, if I find V pi, it need not be Vn plus 1, right. So what 3 is telling me is that V pi is epsilon optimal, what C is telling me is V pi is epsilon optimal, what D is telling me is that Vn plus 1 is epsilon by 2 optimal. Okay. So Pallavi, give me the mark. I have to, no, I never offered them before. Right? This is an offer. Nobody took it. And that's easy enough, right? All you need to do is just been following the multiple times I kept saying that V is not the space of value functions. The very beginning when somebody said V is a space of value function, I corrected you. Of this class, very beginning of this class. Anyway, so let's look at the proofs. Well, A and B are immediate, they follow from Banach's fixed point theorem. So we will start off with C and D, right. So just assume that 3 is met for some n, okay. So n is already met, that condition has been met, right, and that V pi, the pi has been derived from doing this, okay. So pi has been derived from doing this, and now I can use my triangle inequality, right. Does not matter, the then is actually does not matter, right, whether these conditions are met or not. I can take one arbitrary V pi and a V star, and I can use the triangle inequality and write this, because it is just about 3 points in space, right. We talked about how I can keep using the triangle inequality in an arbitrary fashion, because all I am talking about are just some 3 points in space, right. So happens that one of them is V pi, the other one is Vn plus 1, the third one is V star, but this will hold regardless of which 3 points I pick, okay. So here is the tricky thing I want you to look at. So let us look at L pi say I want L pi to act on Vn plus 1, right. I want L pi to act on Vn plus 1, right. So what will be L pi acting on Vn plus 1? Huh?
It's a space of only the pi.
What's that?
It's a space of only pi.
Space of?
What is the metric space of L pi?
Of what?
L pi.
L pi is the operator corresponding to the Bellman equation for pi, right? Start off by, I said last class we left off by saying L pi is a contraction, so that L pi. So L pi is just the Bellman equation operating on Vn plus 1. So what would that be? It will be this, right? This, but instead of argmax here I will have a summation over A pi sa. I will have a summation over A pi sa. But what I have done here, pi itself is an argmax A, right? Just one action. So if you remember, I told you about the deterministic policies, right? So this whole thing will go. I will just replace this with my pi s. Right? This will be expected value of r given s comma pi s. Probability of s prime given s comma pi s, Vn plus 1 s prime. So that will essentially be the L pi acting on Vn plus 1, right. Is it clear? Okay, this is L pi on Vn plus 1. I just read it out. I just write it down as a mnemonic. Expected value of R given S comma pi S plus gamma times summation over S prime, probability of S prime given S comma pi S into Vn plus 1 of S prime. Okay, great. So now the thing that you have to notice, how did I get to this pi S? By using max. I used the max operator over this, right? So if I had done L on Vn plus 1, what would I have obtained? L on Vn plus 1 is essentially this, right? Max, right? This is what this one. L on Vn plus 1 is essentially this, right? So what I have done here, because I chose my pi to be the max action here, so whether I apply L pi on Vn plus 1 or whether I apply L on Vn plus 1, it's the same. Because the pi was chosen to be the max action, right? So I can say that this is equal to, sorry, not equivalent. Yeah. So the two are equal. Okay. Okay, so that makes it easier. Now we are going to start simplifying stuff. Okay, I'm going to take this expression. I'm going to try and simplify that. Okay, I can replace V pi with L pi V pi. Done. Why? V pi is a fixed point, so nothing will change. I can just replace it with L pi V pi. Okay, so now so can I do this? Same application of the triangle inequality as we had before. So the 3 points are L pi V pi, Vn plus 1 and L Vn plus 1. So L Vn plus 1 is just another point in space. Right, so between 3 points I can write this triangle inequality. So this is less than or equal to, actually this is equal to, right. So this is the reduction we talked about here. So from LV I went to L Vn plus 1, I went to L pi Vn plus 1, and from Vn plus 1 I went to L Vn, because that is how Vn plus 1 was generated, by applying L on Vn. Okay, so I have written that. Now I can simplify this. So I have V pi n plus 1 here, V pi minus V n plus 1 here, sorry, and v pi minus vn plus 1 here. So I can take it to that side, simplify things. So I will essentially get okay, that is just the first term. Now we have to simplify the second term. So what is the second term? Just like we did earlier, I have done a repeated application of the triangle inequality. Right. The only tricky thing here is the summation goes to infinity, because only when I repeat this till infinity I will go to v star, right, but that is fine, right, because this is anyway it is a vanishing quantity as we go along, right. So this sum will actually exist. Okay. Limit of a summation. Huh? Yeah. Well, you can think of this as v star minus vn plus 1, right, because I am just talking about the norm, right. So it is v star minus vn plus 1, and then I have written this out. Okay. So this is vn plus 1, that is vn plus 2, then vn plus 2, vn plus 3, blah blah blah, so on and so forth. So what will this be? You only said it will be a limit of a summation, right?
1 by 1 minus gamma.
1 by 1 minus
Gamma? Gamma by 1 minus gamma. Gamma.
Right, so I need to take one gamma out. Okay. So what do we have? So we have the first component is less than or equal to gamma by 1 minus gamma into Vn plus 1 minus Vn, right. But when 3 holds, what is Vn plus 1 minus Vn? Epsilon into 1 minus gamma by 2 gamma, right. So if I plug that in, what will I get? Epsilon by 2. If I plug it in there, what will I get? Epsilon by 2. So I have two components there. So V pi minus V star is less than or equal to epsilon by 2 plus epsilon by 2, which is epsilon, right. V pi minus V star is less than or equal to epsilon. Okay. Well, you have to actually, to complete the proof, you have to do that, but I am asking you to do that. Right. Okay. So what was the other thing that we wanted to show? D. already done, right. So D essentially was to show that Vn plus 1 will be at least epsilon by 2 close, so we already done. So we substitute that here, so we get epsilon by 2, so is that. So Vn plus 1 minus V star is less than or equal to epsilon by 2, and what we are showing there is V pi minus V star is less than or equal to epsilon, okay. So that's basically done. So we have shown this theorem. So essentially what we have here is that value iteration converges with that stopping criterion, it converges to a epsilon optimal policy. So you have to pick an epsilon first. Remember, gamma comes as part of the problem definition. So once you pick an epsilon, you can find a stopping criterion using that expression there, and you are all set. Okay. So there is one other very interesting thing that people talk about from a theoretical analysis of algorithms for solving these kinds of MDPs, right. So it's called the rate of convergence. So I've shown you that it converges, but there's this whole concept called rate of convergence, right. How quickly does it approach, right. So I'm not going to get into a huge discussions on rate of convergence, and like I mentioned with the deterministic policy thing, I'll actually put up a small write up on rate of convergence as well, you can read it. One thing which I want to tell you is that so you can with a little bit of not much, right. So L is a contraction mapping, right. So L is a contraction. So at every iteration, right. So my so what is the contraction factor for L? We did this gamma, right. So for every iteration I can show that my iterates, that is basically I start off with V0, then I take V1, then V2, V3 and so on and so forth. Every iteration I can show that the successive iterates will become gamma closer to V star, right. So I have some, so V1 was some x close to V star, then V2 will be gamma x closer to V star. So if gamma is small, it will converge faster. If gamma is very large, it will converge slower, right. So this is called linear convergence with the rate of gamma, right. So if it falls as gamma squared, then it will be quadratic convergence, right. So but linear convergence with the rate of gamma. So this is essentially the thing. So the interesting aspects, I mean if you want to get into the more into the theory of all of these things, is to start studying the rates of convergence of different algorithms and so on and so forth, which I am not going to get into, but there is something for as an aside so that you can look at it.